in there. Is that pine or cedar?
That's pine. Yeah,
Yeah.
that's pine. Yeah, the place that I work is down here in near Moab. It's
Uh-huh.
Castle Valley, and as I'm kind of hiding out, I've got my office set up down here, and it works out quite well for me. I'm here by myself, so I'm more productive. Except me and the two dogs are more productive. I don't have to deal with wife and teenage daughters, so that's a little easier for me here. And it's not a large place. It's like maybe 1,800 square feet here, but it's kind of this mezzanine area that I'm up on the mezzanine, and there's a kind of a living area down below, so the bedroom and a kind of this nice mezzanine area here. Yeah.
Yeah. Well, that's good. Nice place to get out of the city and be able to focus.
Oh, it really is, and it's quiet. It's really quiet, and there's very little air pollution, and also there's no light pollution.
Oh
There's
yeah. Yeah.
strict regulations here. So, on a clear night, I've got the Milky Way, and I feel like I have it to myself. But no, with 300 other people that feel like they have it to themselves up here too. So,
Yeah. Share the wealth right there.
Oh, what was that? I think you were breaking up at Francisco.
Oh no, I just said, sharing the wealth with that nature beauty down there.
Oh yeah.
Is that classified one of those space viewing or stargazing areas?
Dark sky, dark sky. They're trying to do that. Moab is, and that's just across the river from us. So, I mean, we're in the same place. The only place that we get light pollution is anything that is in our valley itself.
Okay.
Like I say, there aren't that many people here, and we do have strict regulations against outside lighting, no street lights, no commercial lights. I mean, there's none of that. So it's basically what you have are just indoor lights in people's houses at night. And so when people go to bed, it's pretty much completely dark. A lot of people come down here to do night photography for that reason.
Oh, yeah.
But other than the light from Moab, there really isn't any source of light anywhere near. Yeah. And Moab is just getting worse and worse, and more and more lights, and more ATVs. It is like, I don't know. People are getting grumpy about it down here.
I think one time we went down to a hamburger joint down there. I think we were the only ones speaking English. There was a lot of Europeans there.
Isn't that something? Yes. There's a lot of people that come here from all over the world. It's what they say, the big five in terms of the national parks. And of course, Arches is one of the probably the most famous one in Utah. But Zion and there's just Capitol Reef, and it's just like Bryce, and all of those things are down here. So, brings a lot of tourists and spend a lot of time down here. It makes my life a little. It doesn't make much of a difference unless I go into Moab. They don't come here.
Yeah, that's good.
Makes the river a little bit more crowded. I'm only about 3 miles away from the Colorado River, and so I do in the summer. I could take I have my own raft, and it's really easy just to drop it in and take family and friends. We just do a day on the Colorado River, and it's a lot of fun.
Oh, nice.
But that gets pretty crowded, because all the commercial, and that's really a popular place. And so that gets a little crowded, the launching and the off ramp. But other than that, it's great fun. I've got it down.
Oh, that's good. That's nice.
Yeah. So let's see, who do we have on, and what time do we have? Oh, we should be starting here. So who's on here? Let's see, go to participants. Okay, we have 46 people here. I'm just sitting here chatting away with Francisco. We're just missing everybody else. Everybody doing well here tonight? Or today, I guess, this morning?
Yep, just getting up, working out, ready for the day.
Just getting up and getting ready for the quiz, I guess, that is coming up on Friday. I have not put together the quiz yet, but it is going to be essentially simple problems, and probably going to be multiple choice, but maybe a couple of quantitative numbers. Now that I figured out how to do that, the quantitative numbers would again be going back into using steam table values, and there might be a couple of ideal gas calculations that I'll ask you to do. Okay. So basically similar, but I'll keep going back and having you do whatever we do in the context of the energy calculations we're doing, and then using those as a basis, then go to get information in the steam tables. It's always going to end up that way, back and forth, property tables, figuring out that second state. Okay, so anyway, welcome everybody, welcome Awake. So today I wanted to talk about a couple of different things. I wanted to talk about talked a little more about specific heats. We talked about that last time, and we had mentioned a couple of things. One is specific heats of solids and liquids, but I kind of glossed over that. And we spent most of the time looking at specific heats on gases and ideal gases in particular. And the one thing that we want to make sure of is that we understand that just because it's an ideal gas does not mean that its specific heat is constant with temperature. That's true with the noble gases, where the very simple gases, they tend to be pretty constant, but complex molecules also increase in specific heat as you go to higher temperature. And that makes the computation of enthalpy a little bit more difficult. Okay, so, but we talked about that in terms of, and we'll be going into much more detail in looking at enthalpy and getting the numbers out of tables, especially for air. But we'll be getting into that detail when we go to this next level, and that's when we start talking about entropy, right? When we start talking about entropy, then we also need to be using the entropy tables, and those are also documented in the back of the book. So we're kind of waiting a little bit to get into those tables until we get to the sections on entropy or isentropic expansion or compression. But today I just wanted to cover a couple more bases, a little bit more in terms of looking at enthalpy and internal energy and working out some of those relationships a little bit more closely. And then I'm going to spend my time looking at some examples. And so the examples are going to be essentially just problems that I've taken out of the book, but problems that I can demonstrate some of the principles that I'm trying to have you learn in this part of the lecture. Okay, so I'm going to slip on down here, and as always, get a little nervous about going to share screen, but see what I can do. Okay. All right, so today, I guess that's the only thing I have here. So today, I wanted to look at solids and liquids. And in general, when we talk about enthalpy, enthalpy is always going to be defined as being equal to the internal energy plus PV, right? So H is equal to the internal energy plus PV. When we define H, we typically think of this as being equal to like a C sub P times delta T. And delta T is equal to T minus some sort of a baseline temperature, whatever that happens to be. And our value of the internal energy, well, that's a C sub B times a delta T for the same delta T plus PV. When we think about liquids and solids, the question comes up, am I really looking at anything that has to do with a change in the specific volume? In other words, there are some liquids that maybe, if you get close to the critical point, they might change volume significantly with pressure, but in general, we talk about liquids and solids as being incompressible. Yeah, sure, you might be getting a little bit of compression. Sure, you might be getting a little bit of an expansion with thermal expansion. But in general, we just talk about those as having a constant specific volume. And so we're left with thinking, well, what does that mean in terms of doing our energy calculations? Well, one is that if I look at this term here, I might have dH, if I just look at the derivative of this, is du plus P dV plus V dP. And what I realize is that if this volume doesn't change, that's going to be 0. So in a sense, what I'm looking at is if I look at a pump, for instance, and if I have a pump and my fluid that's coming in, excuse me, that's not a very good pump. Okay. I'll draw a pump here. I've got a fluid that is coming here at some P1 and coming out here at another pressure P2, and I'm putting work into it. Essentially, my work is going to be equal to my mass flow rate times H2 minus H1. And that's really by definition. That's 0.2 with H2, 0.1, H1. So if I look at what that difference in H, I have a different possibility. M dot could be due to a change in the internal energy, but it ends up the pumps, unless I have really a lousy pump, and it gets kind of to another point that we're not really talking about quite yet, but if I have a lot of friction, what I'm doing is generating entropy. This pump will not be 100% efficient. But if I make an assumption that is 100% efficient, that means that there's no friction, which means that I'm not creating any heat. So if I'm just putting this liquid from a lower pressure to a higher pressure, I'm not generating any heat. And so my value of dt, my du is not changing. So this just ends up to be a P times, ends up being my V times P2 minus P1. Okay. So all I have is this in my change in H. All I have is my constant specific volume now times a delta P. That means that for that delta H, that all I have is this V times a delta P. Okay. So one of the things we think of for liquids, ideal pump. Okay, that should be a rate is equal to M dot V P2 minus P1. Okay, so that's one of the things that comes from this process. The other thing is that since this term never becomes really significant, P and V, because V for liquids, that thing is really small. And so in general, we'll make the assumption for liquids and solids that under almost every circumstance, C sub P is equal to C sub V, which is equal to just a constant C. We don't differentiate it. This gets differentiated when we start talking about gases. There's not a gas present. It's just a specific volume. We're not worried about this PV term. But we still have the condition of a H, a C sub P delta T, but it's just that we don't have any work on a boundary if I have a liquid, unless that liquid itself is doing the work on a boundary. Okay, so that's the main idea behind liquids and solids. And so if I do something like, say I have a glass of water here, and the temperature, say the mass is equal to 10 kilograms, and say my T is equal to, just take a number, say 25 degrees C. And so I have some sort of energy associated with that. And then I take a sphere, some sort of a ball, a solid, and this has, say, a mass of 1 kilogram and a T equal to 100 degrees C. And I take this and stick it into that container, into that water. What is the final temperature? Okay, so this is a condition where it's really quite simple. We're just doing energy balances on the water and on the solid. So here is an example of that. And what does that energy balance look like? Well, what we really don't know is what? I mean, what are we looking for? What's going to happen if I let this sit in there for an hour?
It would probably cool off.
It would what?
Sorry, I just said you'd probably get some kind of equilibrium.
Yeah, you'll get to some equilibrium. Let's put a little bit more. Let's say this is insulated. I don't want to worry about a cube. This is adiabatic. Okay. So if it's adiabatic, then the energy initially has to be equal to the energy at the end. And that should give me enough information to be able to specify what the temperature is, the final state temperature, right? So if I look at the energy at the beginning, I have E1, which is equal to the mass of the water times C sub P of the water times T minus, and I'll set my baseline at anything that can be arbitrary here. I'll just say Ti, whatever that initial temperature is. Plus, I have the mass of the solid times the C sub P of the solid times its temperature minus its initial value. Okay, so this is the amount of energy, and that has to be equal then to what? Energy final, right? And maybe I better back up just a little bit. I think this might be confusing. Let me just back up a little bit. I realized that my nomenclature could be a little bit different here, and this would be a little less confusing. And this will work, but oh no, my equation's disappearing. Okay, C sub P water and mass of water times T 1 plus mass of the sphere, C sub P of the sphere, times T, this is water 1, and this is the sphere 1, and that has to be equal to E2, which is equal to the mass of the water times C sub P of the water times T2 plus mass of the sphere, C sub P of the sphere times T of the sphere at point 2. Okay? And then we recognize that that is the same as that. And then we have those initial values. And so what this allows us to do is to then write out some sort of a relationship between the mass of the water and C sub P, C of water. We'll just drop the P. And then this will be T water at 2 minus T water initially will be equal to the mass of the sphere times the specific heat of the sphere times T sphere initially minus T sphere 2. And T sphere 2 is equal to T water 2. Okay, comes to equilibrium. So you can write out these energy equations, and then this allows me, by looking at the temperature drop and the specific heat of the water and the mass of the water, to relate that to what I'm going to be seeing in the drop of the temperature of the water. The water is going to end up to be about 20-something degrees for these conditions. Okay, so you want me to go a little bit farther on this, or are you okay?
I was going to say, that last T, what is the subscript on it?
Oh, TS. Yeah, let me clean this up a bit for you. Maybe clean it up a little bit too much for you. S2. Okay, so TS2 is the same as the water 2. They're going to come to the same point, same temperature if I wait long enough. Okay, so this is the way that we're going to be using the energy balances and using the energy balances for liquids and solids. We just take those values of the specific heats as being constant. Want me to go one step further on this and do a calculation, or are we good with it?
Hey, Professor, quick question.
Yes.
I've always struggled with determining, and I think you kind of explained it a little bit already, C sub P and the use of C sub V. Now, in this particular case, could you have used C sub V also too, since we're saying it's equal to C sub P?
Yes.
And C?
Yes. Always for liquids and solids. Always for liquids and solids. We have to differentiate them when we start looking at gases and two-phase systems.
Okay.
For a two-phase system, it doesn't make any sense anyway, does it? Because things are vaporizing and not changing temperature.
Mm-hmm.
But for we're really talking about gases, and for the gases, it's where you have the most problem with differentiating between a C sub V and a C sub P.
Yeah.
And for this class, it's very simple: is you stick with C sub V for a fixed mass system, like in a piston.
Okay.
Then you're going to be okay. C sub P is related to an enthalpy change, and you'll be using that when you're looking at something like a pump, right? So here I use a difference in H, and delta H is always C sub P, delta T, right? Okay. So here I'm looking at, or just a delta H be a C sub P. So in these cases where I'm looking through a flow system, I think of things in terms of enthalpy. And in this case, for incompressible fluids, your difference in enthalpy just ends up to be the specific volume times the difference of pressure.
Okay.
And for this problem here that we're working through, these are just C's. We don't care. This is just a specific heat, kilojoules per kilogram K. It doesn't matter because it's incompressible. We don't change the volume. And that PV term, these volumes, specific volumes, are really very small compared to the energy that we're keeping thermally. We just don't even worry about that part for liquids, not for fluids. Fluids include gases, but just for liquids.
Okay.
So we just work through this just a little bit more. Let's do this. So we have mass of the water, seawater, times, and I have T water, 2, and then I'm going to bring this over TS2, and that is multiplied by MSCS, and that is going to be divided. Let's see, let me just back off here just a bit. Okay, let's finish this off. So I've taken care of that term and that term. So I have MSCS, TSI, and then I have this term left, which is plus M water, C water, T water, I. And this is T water 2, the same as TS2. Okay, so what we end up with is, if I'm wanting to look for this value of T water 2, this is just a weighted average, the mass weighted average of the two different baths. Excuse me.
So would it not be 2 times that because you're adding them together?
I think that's going to end. I think I might made a mistake there. Just one moment. Let's see. I have added.
Oh wait, never mind, because you factor it out. No, I see.
I think that should. Yeah. I'm doing kind of a mass averaging of those. Yes. Okay. So anyway, that's how you use specific heats, and again, using simple energy balances like energy balances here, doing that directly with specific heats. The only thing they're changing here or temperatures. Okay, let's look at a couple of problems. Let's look at this problem here. A spring-loaded piston cylinder device, 1 kilogram of carbon dioxide, and the system is heated from 100 kPa and 25 degrees to 1,000 kPa and 300 degrees C. Determine the total heat transfer to and the work produced by the system. First of all, what might this look like on a PV diagram? I always like to draw a PV diagram. I have an idea of what areas I'm integrating under and that type of thing. So let's look at a PV diagram on this. So I start off at some point out here. And at this point, it's 100 kPa. So this is at atmospheric pressure. Looks like that weight is just hanging off that spring for the most part. And 25 degrees. And I have a 1 kilogram. So I know, how would I know the specific volume for that? I think you have to go to
steam table on that one, or
yeah, the CO2 superheat. Is there CO2 superheat table, right? Because that's where I am. I'm at 100 kPa, 25 degrees. Okay, and up to 300. I don't think I'm above the critical point. So is that superheat? Get out your books if you have them. Yeah, that is superheat. And so I'm going to be using the ideal gas laws. Okay, so our ideal gas law is going to be PV is equal to RT. And I'm assuming that this range of temperatures and pressures will not put me near the critical point. So I have this relationship here is PV is equal to RT. We also have an energy equation, which is EN minus E out is going to be equal to the change of the energy in the system. And the energy in is Q, and the energy out, it'll just put as work, boundary work as they use in the nomenclature in the book. And that's going to be equal to the change of the energy in the system. Well, what is the change of that energy into the system? It's a closed mass, right? So how do I define the change of energy in that system? Just change of internal energy, right? So the change of internal energy is going to be mass. And since it is a fixed mass, I'm going to ask Francisco to tell me if that's a C sub V or a C sub P.
So that would be a C sub B?
Exactly. That's a C sub V. I have a fixed mass. And then what I'm looking at is the difference in temperature. So it's going to be my temperature 2 minus temperature 1. That's going to be the change U2 minus U1, right? There's going to be mass.
Why it was a C sub V, not a C sub P?
This is a fixed mass. This is just, for a fixed mass problem, you always go to a C sub P. Oh, excuse me. I always go to a C sub V. C sub V for fixed mass. When you're looking at a flowing system, steady state flowing systems for gases, multi-phase flow, it's a C sub P. But for the case of a fixed mass, you assign them with a C sub V. Okay.
So like with a nozzle or a turbine, we're looking at C sub P.
Right.
But fixed mass, even like a rigid tank, closed bottles, that would be like a where you don't have anything coming in or out. It's just a C sub V then.
Yep, exactly.
Yep. Okay.
Exactly. Okay, so there's a relationship, and we have a couple of different pieces of information, temperatures and pressures, but we can see that we've got a change in temperature, but we don't know what that work of the boundary is. So we've got to work out the boundary. And so as we think this through, we have temperatures and pressures on either side. So we're in pretty good shape there. We don't know that change in volume. We're going to have to work out what that volume would be. And then we're going to have to think out whatever relationships tie us from point 1 to point 2. Well, what is tying us to point 2? Well, we're pushing that thing up against a spring. So if I have any displacement, if I make this if I increase the pressure, I'm going to decrease the volume, but it's going to do it in a linear way because of that spring. So I know that if I add heat to this, I'm going to increase the temperature and increase the pressure. But I'm expecting that what I'll be seeing is some sort of a relationship that goes like that. But it's going to be linear. And so we'll just take that as my point 1, and this being my point 2. This starts off at 100 kPa, and this ends up at 1,000. And I'd like to know what this value is, V1, and I'd like to know what that value is, V2. Well, V1 is going to be equal to MRT over P1, which is equal to 1 kilogram times my value of R. My value for R for carbon dioxide is 0.1889. And this has kilopascal per kilogram K for units if we wanted to look those up, times T, and T is given to us as a value of 25, which is 298, right? I'm multiplying by a temperature, so I have to use the absolute value. And then I divide by the pressure, which is 100 kPa. And that will give me a volume of 0.5629 meters cubed. V2, the same mass, RT over P2. And I still have this 1, and I still have this value of 0.1889. And I have a value of 573 because I've gone to 300. 273 plus 300 is 573. That's K. And then I divide by the pressure, which is 1,000 kPa. And that gives me a volume of 0.1082. So then the only thing that's left is to calculate this work. So now I have this volume fixed and that volume fixed. So I've got this guy and I've got this guy. So really, to be able to get the area under that curve, which is really what I'm looking at for my work at the boundary, all I have to do is take the area of that trapezoid, right? So I'll just move this up a little bit to get a little bit more working space. And so my work of the boundary is going to be equal to P1 plus P2 over 2, right? So that's going to be my average pressure times the difference in the volumes. The difference in the volumes are V2 minus V1.
Professor, can you explain how you determined that it was superheated and therefore you could use the ideal gas equation?
Well, first of all, we don't see carbon dioxide at atmospheric temperatures and pressures as being anything other than just a gas. And then we think, well, what would happen if I increase the temperature to 1,000 kPa and heated it? Would it put me anywhere near the critical point? And the answer to that is no. So we know that it's going to be a gas, and we know that it's not going to be a liquid. We're really not at low temperatures or extremely high pressures, so it's not going to be a liquid. We know it's going to be a gas, and we don't. And let's look at what other information we have on carbon dioxide. We have its critical point. That's another piece of information.
I was looking in the appendix of A20 where the CO2 tables are.
Yes.
And unlike the other tables that we've been recently looking at, it didn't seem to have like the superheated region or the saturated gas region. Or
that's because the table you're looking at there, Chase, is actually already assuming it's superheated. This is the ideal gas stuff.
Yes.
Okay.
Yeah.
So we can assume with CO2 that it's got to be superheated.
Everywhere, and unless we start talking about something in these really high pressures, CO2 is going to work as an ideal gas. And so, in general, in this class, if I'm talking about a gas, just assume it's an ideal gas. You don't have to think too much about it. There might be a little discrepancy when you're really close to the saturation line for steam. But for this class, if I'm talking about a gas, I'm talking about it being an ideal gas. The only place that it's not going to behave as an ideal gas if I have phase change. Okay, so towards the end of the semester, we'll have problems where I have a gas, dry air, and I have phase change where I'm doing something like injecting liquid water and getting the water to vaporize. Then even the air still works like an ideal gas, but at that point, we can't quite think of it totally as ideal gas because there's a phase change process that is going on. If there's no phase change going on, don't worry about it being an ideal gas. I mean, anything but an ideal gas, right? We worry about it being an ideal gas if you're close to the critical point or if there's phase change. Other than that, air is not a pure substance, but we're not close to the point where either the oxygen or the nitrogen is going to condense out. We're not at those very, very low temperatures and very high pressures that would get that to happen. So, every gas we talk about in this class, with the exception of maybe a little water vapor that's vaporizing and condensing, think of everything as being an ideal gas and you'll be fine. Think of every closed container as being represented by a C sub V. Think of every open system like turbines and nozzles and pumps as being related to a C sub P, and you're going to be fine. All right. Thanks for all these questions. These are good.
Thank you.
Okay. So this is what we have. We can take an average pressure, and at average pressure, that gives me the same area in this curve as what we would get from the area in this curve. Okay, so I've just got this relationship for that work. And with that relationship, I have a given amount of energy that has been done as being minus 250.1 kilojoules. And why is that? Well, V2 is greater or less than V1. So
just want to double check, Professor.
Yes.
The V2 and V1 in that bottom equation, those are specific volumes, right? Not total volumes we calculated.
No, those are total because I've got the mass. So these are meters squared or cubed. Yes.
I mean in the work boundary equation. So we have the V2. Are those supposed to have a line through them? Or are they the specific volumes?
Oh, I just put this as a specific volume, but these, if I just multiply by the total mass, which is 1, these are the same because I've got 1 kilogram, right? So the specific volume or the total volume. In this case, they're the same because I've got 1 kilogram of carbon dioxide. But I just did this as total volumes using that 1 to be able to get that total work.
So if we had a problem that wasn't 1 kilogram, would we be expected to do total volume or specific volume in that bottom equation? So I'm just trying to, in case I get a problem like this later, I'm trying to figure out which.
Well, yeah, they're the same. Of course, this is M times V2 minus V1. So in a way, they're the same. It's just that if in this case I've carried this 1 along here, if I didn't have the mass, I could have just done this in specific volume because the specific volumes are what's really changing. Again, that defines your state. And if I have the mass, and so this is arbitrary, the way that I'm doing it with a specific volume, but specific to a mass is where I put in the actual mass and get a total volume. I could have done this per unit mass all the way through and not had this mass in here. And then this would have been a specific volume. And then work, the boundary, would have been mass times like P average times delta, I'm running out of room here, then V2 minus V1, right? It would have been the same because I still had that same mass that I would have then multiplying at the end. So I just did it a little bit earlier to get the total volume versus the specific volume. Does that answer your question?
Yes.
Okay, and be careful on this. Your P's have to be in kilopascal, and then your volumes have to be in cubic meters to get your units right for kilojoules for the workout. Okay, so that's that part. But what does that mean now in terms of the total heat transfer? Okay, we've calculated the total work. Okay, but what's the total heat transfer? Well, we go back to this equation here, don't we? It's our energy equation. And now we have our work and we have our delta T. We know everything we need to know to make this calculation. So let's do that. Q then is going to be equal to the work of the boundary plus M C sub V T2 minus T1. And that's going to be equal to minus 250 plus 1 kilogram. And the specific heat is carbon dioxide 0.067. And then a change in temperature, T2 minus T1, is 300 minus 25, which is 275. And that will give me a total heat transfer of 69.4 kilojoules. Okay? Is that making some sense? Okay, let's go on to the yes.
Is that second term of what Q equals, the work of the boundary plus the MC yada yada, is that second term for just the internal energy of the mass?
Exactly.
Okay.
Yeah. And it goes back to this first equation here. The energy in minus the energy out is the change of energy in the system. The energy in is Q. The energy out is minus boundary work, assuming that it's in that direction. And then that's going to give us this change in temperature, change of the internal energy, which is just a change in temperature. Because I'm not changing its kinetic energy. I'm not changing its potential energy. All I can do is change its temperature. And so that's my energy equation. And then the next piece is, well, I know that delta T. To get Q, I've got to figure out how much work gets done. I was a little surprised when you look at this to realize, oh, the volume gets this actually gets compressed a little bit. So the volume at the end is less than the volume at the beginning. Anyway, that was, but once you have the work, then you could put, and I can do that relatively easily if I have something like a spring. If I draw these pictures out, so I realize, oh, here's my spring. This is what it's going to look like, and then I just take the trapezoid rule to get that right for the area. Once I have my work, then I have everything I need to be able to calculate my Q. Okay, typical problem. Any questions on that?
Professor, I don't see that C sub V value. So I'm looking at table A2.
Oh, yeah, I think I actually put in the wrong number here, didn't I? I'm looking at this as, yeah, those are properties from table 2A. A2A.
Yeah, I see 0.657 for CV.
Yes.
You have 0.067, I believe.
Let's see, carbon dioxide 667. Oh, 657?
Yes, sir.
Okay. Thanks. Okay, is that making sense?
Not really.
Not really. Oh no. Oh no. Let's go through all the steps again.
No.
Let's go through all the steps again. We have conditions at the beginning and the end, temperatures and pressures. So we define the states. We have the total mass. We looking at CO2, and we make the assumption, and no reason why we wouldn't think it is going to behave as an ideal gas. So we have an ideal gas that's going to follow this relationship here. PV is equal to MRT. That's one of the relationships we need. Another relationship we need to be able to look at the total work and the heat transfer is the energy equation. Q minus work in the boundary is equal to the mass times C sub V, T2 minus T1, and C sub V. We're using C sub V because we have a fixed mass. We're asked to get WB and Q. And we're given those two values. We've got everything we need to know here. But we need to have relationships where we can calculate the work on the boundary. And then from the work on the boundary, I can calculate my heat transfer just by looking at this equation. I have delta T. If I know the work on the boundary, I can calculate my heat transfer. So the question becomes, how do I get the work on the boundary? And I'm doing that by starting off with a PV diagram, because I know the work on the boundary is going to be area to, if I look at what that pathway is from point 1 to point 2, that I know that my work is going to be equal to the area under this curve. Okay, so my area is going to be equal to P1 plus P2 over 2 times V2 minus V1 times the mass. Okay, and that's because we said, oh, the volume or the area under that trapezoid is the same as the area under that square. So we take the average pressure, then multiply it by the difference in the specific volume. This gives me a way then directly of calculating the work, which is then specified here. All right? Average pressure times the difference in the volume. That gives me the work. Now I have the work. I can calculate the amount of heat, and I go back to my energy equation. Now that I know my boundary work, I bring it to the other side of the equation where I have all of these are knowns: the work on the boundary, the mass, specific heat, constant volume, and a difference in temperature. That help?
Yes. Did we ever calculate mass in relation to that work solving for work boundary?
Did we ever calculate the mass? No, it was given to us as 1 kilogram.
Oh, sorry. Then that's why it's more. Yeah,
Yeah.
Makes sense.
No problem.
Cool. Thank you, sir.
All right.
Professor, how does
Yes.
the spring play into this problem?
Well, the spring is what's giving me a linear response between pressure. It gives me a linear force on that piston. So any way that piston moves, it's going to be moving in a way such that the force is going to be equal to pressure times the cross-sectional area, right? So whatever the pressure is just whatever the force is on that spring divided by the cross-sectional area. And that force is typically going to be equal to some sort of a spring constant times x minus xo divided by the cross-sectional area. So we know that there's been some initial location xo, and so we know that this is going to be a linear response with x. If I change x, my volume, or my change in volume, is equal to my area times the change in x, right? So if I'm changing x, I'm changing volume. So I kind of know that this is happening. And if I know that is happening, I know that my pressure is going to be changing linearly with specific volume, because that spring constant is going to change linearly with deflection. So whatever that force is that is being exerted on that top cylinder, I know that I'm going from this point to this point, and that pathway is linear. Okay? That's really the main point of the spring, is saying that my pathway is linear. Oh no,
Professor,
this tells me I'm out of time. Yes.
do you have a unit issue at the end there of that problem? It should be kilojoules, not kilograms in your final answer, right?
Oh yes, that's true. Thank you very much. Yeah, let me fix that.
One more question on the heat added
Sure.
to the system, because technically the answer is negative, but we're saying the question is asking how much heat is being transferred to the system, so that would have to be a positive 69.4 kilojoules. Is that how, is my understanding of that right?
I'm adding that amount of heat. Yeah.
Yeah, because it's asking. Otherwise, it'd be heat coming out of the system. If that was the question, right? How much heat?
That's true. That's
Okay.
true. Yeah. So yeah, I mean, it is kind of interesting to be looking at this problem, because what I realize is that it's kind of counterintuitive, isn't it? I'm adding heat to this, and it's actually, the spring is actually compressing.
Yeah, and it's kind of the same thing too with the negative work value.
Yeah, exactly. Yeah, so that spring has done work on the system. Yeah. So that is a little bit counterintuitive, but those again are the steps, and it really highlights some of the main points that I want to be making. When you're looking at these systems, just start off, draw this on a PV diagram that you feel comfortable with, and then just write an energy equation. Just get the correct energy equation, and then the rest is just looking at properties, right? Just properties. You're going to have to do something to get a value for work, that integral, whatever that happens to be. But you just have a relationship for work. If you know the path, you can work that out. All right. So I'm out of time, but I'm going to stick around here. There's no additional information I'm going to give to everybody, but if I'm willing to stick around for as long as it takes for people to answer any questions. Okay. So there's no need for anybody to stick around, and I'll get this lecture and clean it up and get it online probably this afternoon.
Thank you, Professor.
You're welcome.
Thank you, Professor.
Yeah, and actually I'll go through the rest of the lecture too. I've got a couple of other examples that I wanted to look at, but I'll get those up and make sure that you have an opportunity to look.
Thank you, Professor. Appreciate your help.
Professor, may I have a